Good morning to everyone. My name is Dr. Tirupati Venkateswara Reddy. Today we are going to see the problems on Norton's theorem. So the first problem is the example one is find the Norton's equivalent circuit for the network in the dotted area of figure and then find current through the 10 ohm resistor. So this is the network they given. So in this network, they are asking to find the equivalent circuit, Norton's equivalent circuit. So for the whatever the dotted area, and also they are asking to find how much current is passing through the 10 ohm resistor. So coming to the solution, first understand the problem, what data they given. So once we understand the problem very clearly, from that we can find very easily what are the requirements, what are they are asking, that we can find very easily. So I'm suggesting to everyone, first understand the problem, from that you can write the given data. So what's they are asking in the problem? So the Norton's equivalent circuit. So in given data I'm writing the Norton's equivalent circuit question mark. Second one, they are asking find current through the 10 ohm resistor. So that is current through the 10 ohm resistor I10 over IL equal to question mark. So how to find the current through the load resistance? Already I explained in Norton's theorem how we are calculating current through the load resistance. For that, what are the steps we are followed? Already explained in the Norton's theorem. So the same steps here we are going to follow. So the step one, to determine the current through the load resistance RL. So temporarily the load resistance I am removing from the terminal A and B, and it is shown in below figure. So this is the figure. So the second step is determination of short circuit current or Norton's current. So how to calculate the short circuit current or Norton's current? So in order to find the short circuit current or Norton's current between the terminals A and B, so by short circuiting the load resistance RL, and also we have to keep all the sources in original position. That means whatever the sources they given in the network, so those sources we can keep it as same. We could not change anything here. Only thing is we have to make it the load resistance is short circuit here. So this is the network. Here I done the short circuit. So if you observe this figure, here the 2 ohm and 6 ohm are connected in parallel. Then the resistance is 6 into 2 by 6 plus 2. So that is equal to 1.5 ohm. So now these two resistances, that means 2 ohm and 6 ohm, I am replacing with the 1.5 ohm. Why? Because these two are connected in parallel. Now the circuit is, so this is the circuit. So if you observe this figure, here 3 ohm and 1.5 ohm are connected in series. So then the total resistance 3 plus 1.5 is equal to 4.5 ohm. So now this 3 ohm and 1.5 ohm are replaced with the 4.5 ohm. Now the circuit is this one, 9 volts and 4.5 ohm. So if we observe this circuit, here we know that 9 volts as well as we know the resistance. So once if we know the voltage, once if we know the resistance, so from that we can find how much current is flowing through here. So according to the Ohm's law, I equal to V by R. So now we know the V value as well as the R value. So V is 9 volts, R is 4.5. So the current is 2 amps. So because of 9 volts, 2 amps of the current is passing here. So the 2 amps of the current is passing through the 3 ohm resistor. So once it is reached to this node, so this 2 amps of the current is splitting into two ways. So some amount of the current is passing through the 2 ohm and some amount of the current is passing through the 6 ohm. But here we need to find how much current is passing through the 2 ohm resistor. So now short circuit current or Norton's current. So whatever the current is passing through the 2 ohm resistor, that is the short circuit current or Norton's current is equal to, so the total current, that is 2 amps into, so what is the opposite resistance for here for this? So 6 ohm, because I am calculating how much current is passing here. So that's why opposite resistance is 6. 6 by, so sum of the resistances 6 plus 2 is equal to, so 2 into 0.75 is equal to 1.5 amps. So this is the short circuit current or Norton's current. So if you want to find how much current is passing through the 6 ohm means, so the total current into opposite resistance. Here the opposite resistance is 2 by the sum of the resistance is 2 plus 6. So when you are calculating how much current is passing through the 6 ohm. But here we are going to find only the short circuit current. That means how much current is passing through the 2 ohm resistor. That only we are identified here. So now we know short circuit current as well as the Norton's current. So in step 3, we are going to determine the Norton's resistance. So here, the Norton's equivalent resistance of the network as seen from the terminals A and B. When you are calculating this Norton's equivalent resistance, if any voltage sources are there, that voltage sources can make it as a short circuit or replaced by their internal resistances. If any current sources are there, those current sources we can make it as a open circuit. So based on these statements, now I draw the circuit because in the given network, they given only one voltage sources. As per this statement, that voltage source I make it as a short circuit. And here I am calculating the Norton's resistance from the AB terminal. I am seeing from the AB terminal. So if you observe this figure, here 3 ohm and 6 ohm are connected in parallel. Then the resistance is 3 into 6 by 3 plus 6, that is equal to 2 ohm. So now this 3 ohm and 6 ohm are replaced with the 2 ohm resistor. Now the circuit is 2 ohm resistor connected in series with the 2 ohm resistor. So now if you observe this figure, this 2 ohm and this 2 ohm are connected in series. So then the resistance is 4 ohm resistor, 4 ohm. So this is the Norton's equivalent resistance. So now we know Norton's current as well as the Norton's resistance. So once if you know the Norton's current, Norton's resistance, so we can easily draw the Norton's equivalent circuit. So in step 4, so draw the Norton's equivalent circuit. How to draw the Norton's equivalent circuit? So by replacing the entire network by a Norton's current or short circuit current in parallel with the Norton's resistance. And it is shown in below figure. So this is the equivalent circuit. So already we calculated the Norton's current. So that Norton's current is 1.5 ohm, as well as we calculated the Norton's resistance, that is 4 ohm. So in step 5, here I am connecting the load resistance back to its original position. From where I removed, there I am connecting. So I removed the load resistance initially from the AB terminal. That same resistor I am connecting to the back. So that is shown in here. So the load resistance RL I am connecting back to its AB terminal only. So in step 6, here to determine the current through the load resistance, how much current is passing through this load resistance, I need to calculate. So I need to calculate how much current is passing through the load resistance. So by applying current division rule, so the load current IL equal to the total current, that is Norton's current into, so for this opposite resistance is Norton's resistance divided by Norton's resistance plus load resistance. So now the Norton's current is, that is the total current, 1.5 amps into 4 by 4 plus 10 is equal to 1.5 into 0.2857. So now the load current is 0.428 amps. So this much of current is passing through the load resistance. So in the given data, they are asking to draw the equivalent circuit. So that already we done. We drawn the equivalent circuit here. So this is the equivalent circuit we drawn. So on the second one, they are asking to calculate how much current is passing through the load resistance. So that current also we calculated here. So 0.42 amps of the current is passing through the load resistance. So now we know the load current as well as we know the load resistance. So once if we know the current and resistance, so what is the drop across this load resistance that we are going to identify? So the voltage drop across the load resistance or the potential difference across the load resistance is VL equal to IL into RL. So now we know IL as well as the RL. So IL is 0.428 amps as well as RL they given, that is 10, is equal to 4.28 volts. So this is the voltage drop across the load resistance. So this is about the problem. In upcoming videos, we are going to see the more number of problems related to the Norton's theorem. Thank you. Thank you so much.